Let's begin with the big picture of aluminium extraction. Imagine bauxite ore as a locked treasure chest containing aluminium compounds mixed with iron oxides, silica, and titanium oxide. The journey from this raw ore to pure aluminium metal is like a relay race. Each stage prepares the material for the next. We start by upgrading the ore through beneficiation, then dissolve it in caustic soda in the Baer process, clarify the solution, precipitate aluminium hydroxide, and finally calcine it to alumina. The alumina is then fed into the Hall Herold cell where electricity, not just chemicals, becomes the ultimate reducing agent. Every step has its own purpose: better purity, lower energy, and higher efficiency. So, by the time we tap molten aluminium from the electrolytic cell, we've turned red, earthy rock into shiny, silvery metal ready for industry. Now, why do certain metals get the luxury of being free? It's all about reactivity. The noble metals like gold, platinum, and silver are so unreactive that they can exist without combining with anything else. You might have heard of alluvial gold, those shiny golden flakes carried by rivers and collected in sands. These metals don't tarnish easily, they don't corrode, and they have such high reduction potentials that nature itself fails to attack them. That's why your grandmother's gold bangles can stay bright for decades without rusting. The native occurrence of metals is nature's way of telling us here is the ultimate standard of unreactivity. Let's step into the combined world of metals. The highly reactive ones cannot survive free, they immediately lock themselves up as oxides or carbonates. For example, aluminium is found as hydrated aluminium oxide, written as Al2O, which we call bauxite. Calcium prefers the carbonate form CaCO or limestone, and zinc is often found as ZnCO called calamine. When carbonates are heated strongly, a process called calcination, they decompose into oxides. For instance, MCO breaks down on heating to form more plus carbon dioxide gas. That is why we see bubbles of gas escaping when certain mineral samples are roasted in the lab furnace. So, if you find an ore fizzing out when treated, you're most likely holding a carbonate. Another important group of ores is sulfides and halides. Lead occurs as PbS, called galena, zinc as ZnS, sphalerite, and iron as Fe, also known as fool's gold or pyrite. These sulfide ores are usually found deep underground, where reducing conditions protect them from oxidation. On the other hand, halide ores like NaCl or common salt and KCl, called sylvite, are formed in dry, evaporated seabeds. Carnallite is another halide ore with the formula KCl.MgCl.6HO. Imagine an ancient salty sea drying up in the sun. Layer upon layer of salt deposits would form, eventually giving us these halide ores. So, climate and geology both play a huge role in deciding how metals are stored underground. Now, here comes the clever part: metallurgists classify ores according to the reactivity of the metals. Why? Because this tells us the easiest way to extract them. Highly reactive metals like sodium, potassium, and calcium are usually trapped as chlorides or carbonates. These need energy intensive processes like electrolysis for extraction. Moderately reactive metals such as zinc and iron occur as sulfides or oxides, and we can reduce these with carbon or heat after converting sulfides into oxides. Finally, the least reactive ones, such as gold and platinum, occur natively, and we can separate them with minimal effort. So, always remember, the type of ore is nature's clue to the right metallurgical method. Let's do a quick calculation to test our understanding. Suppose you have 51 grams of bauxite, which is Al0.2HO. How much pure aluminium can you extract? Here's the key reaction: 2 moles of aloe produce 4 moles of aluminium metal and 3 moles of oxygen gas. The molar mass of aloe is 102 grams. So, 2 moles weigh 204 grams and give 4 moles of aluminium, which is 108 grams now. 51 grams of bauxite is 1/4 of 204, so it will give 1/4 of 108 grams of aluminium, that is 27 grams. Isn't that neat? Always make sure your stoichiometry follows the balanced equation, or you'll end up with wrong yields in the exam. To wrap up, let's link metal occurrence to industries and our environment. Aluminium from bauxite is the backbone of aviation, packaging, and even kitchen foils. Iron ores like hematite and magnetite feed our steel plants, shaping skyscrapers and railways. Salts like halite and sylvite form the raw materials for chemical industries and fertilizers. In India, major ore belts are spread across Jharkhand, Odisha, and Chhattisgarh, which are mining hotspots. But here comes the catch: overmining leads to deforestation, soil erosion, and depletion of groundwater. So, while metal ores are vital for development, sustainable mining is equally important. And that's the big picture. The chemistry of how metals occur in nature is not just about formulas, it's about shaping civilizations while caring for the planet.